Okay, let's look at a few different types of angles. You might recall some of these back from your days of geometry. Classifications. We have acute angles. Acute angles are going to be angles that are between 0 and pi over 2 radians. Remember, in precalculus and in calculus, we need to get comfortable working with radians. This is the equivalent of angles between 0 and 90 degrees, all right? 0 and pi over 2 radians. We also have obtuse angles. Obtuse angles are angles between pi over 2 and pi radians. So that would be the equivalent of angles between 90 degrees and 180 degrees. Complementary angles. Complementary angles are two positive angles whose sum is pi over 2. Two angles that add up to 90 degrees or pi over 2 radians. Here is an example of what would be two complementary angles, the angle alpha and the angle beta. Notice that if I add those two angles together, alpha plus beta, I am going to get pi over 2. Supplementary angles, on the other hand, are two positive angles whose sum is pi radians. They add up to 180 degrees. All right, so here I have the angle alpha and the angle beta. If I add those two angles together, I am going to get pi. So let's see if we can't do a little practice here. Find the complement of the angle theta is equal to 2 pi over 5. Now, one thing to make note of is that it's always helpful in trigonometry to draw out a picture. All right, 2 pi over 5, 2/5 of pi. That is slightly less. 2/5 is slightly less than 1/2 pi. All right, 2/5 pi is slightly less than 1/2 of pi. Therefore, this has to be in the first quadrant. So here I can draw out a quick sketch of what my angle is going to be. Here I have theta is equal to 2 pi over 5. Notice again, whenever you guys draw out your angles, have that initial side on the positive x-axis and the vertex of the angle is at the origin. Okay, so complements. Complements are going to add up to pi over 2. So the complement is going to be this angle right here. Well, that's what we're trying to find. If we're trying to find an unknown, don't be afraid to give it a variable label. Let's call it beta. So we know that complementary angles have to add up to pi over 2. That means beta plus 2 pi over 5 must equal pi over 2. We've set up this algebraic equation, and we can now solve for beta by subtracting 2 pi over 5 from both sides of the equation. Beta is equal to pi over 2 minus 2 pi over 5. Subtracting fractions. All we have to do is get a common denominator. My least common denominator in this case is going to be 10. I multiply my first fraction by 5 over 5. That gives me 5 pi over 10 minus, I multiply my second fraction by 2 over 2, minus 4 pi over 10. And 5 pi over 10 minus 4 pi over 10 gives me pi over 10 for my complement. All right, find the supplement of the angle theta is equal to 2 pi over 5. Well, again, here is my angle 2 pi over 5 in the first quadrant. The supplement of that angle would be this green angle here. Let's call that alpha, all right? And we know that supplements have to add up to pi radians. So alpha plus 2 pi over 5 has to equal pi. In order to solve for alpha, all we have to do is subtract 2 pi over 5 from both sides of the equation. Alpha is equal to pi minus 2 pi over 5, and now I can get a common denominator once again. In this case, my least common denominator is going to be 5. I multiply this first value by 5 over 5. That's 5 pi over 5 minus 2 pi over 5 gives me 3 pi over 5 as my final answer for the supplement. Right, so that's finding complements and supplements. Coterminal angles. Angles are said to be coterminal if they have the same initial and terminal sides. In other words, they start in the exact same place and they finish in the exact same place. Right? So here I have an angle theta. This angle right here, alpha, is considered to be a coterminal angle. Notice they share the same initial side and the same terminal side. Are there other coterminal angles? Yes. Here's an example of another coterminal angle. The angle beta starts in the exact same location and terminates in the exact same location. So beta, alpha, and theta are all coterminal angles, and in fact, there are an infinite number of coterminal angles. We could continue to find angles that start in this exact same location and do however many rotations we wanted to until we get to this terminal side. And we could do that both going in the clockwise or counterclockwise direction. Algebraically, to find coterminal angles of a given angle theta, all we have to do is add or subtract any multiple of 2 pi. That brings us back to our exact same terminating side because 2 pi is the equivalent of one complete revolution. So to find coterminal angles, I take my given angle theta and I add or subtract any multiple of 2 pi. So that's 2 pi n, where n is an integer. All right, so we can add 2 pi, 4 pi, 6 pi, 8 pi, 100 pi. Okay, you can plug in any integer for n, and that will allow you to get a coterminal angle. So find two coterminal angles to the given angle theta, one positive and one negative. Again, to find coterminal angles, all you have to do is take your given angle and add or subtract any multiple of 2 pi. Any multiple of 2 pi times n, where n is an integer. So let's start off by finding one coterminal angle. And our given angle here is 7 pi over 3. To get a positive angle, we could very easily just add 2 pi. 7 pi over 3 plus 2 pi, I get my common denominator. 7 pi over 3 plus 6 pi over 3 gives me 13 pi over 3 as a positive coterminal angle. There I have 13 pi over 3. So notice what I did is I had 7 pi over 3, which is in blue here, and then I just completed one more full revolution. I added on another 2 pi. That gave me 13 pi over 3. All right, let's find another coterminal angle, and in this case, let's find a negative one. So if we're going to find a negative coterminal angle, that means we need to subtract a multiple of 2 pi. Well, notice that because our given angle is greater than 2 pi, subtracting 2 pi is not going to give me a negative value. Instead, we have to subtract the next multiple of 2 pi, which would be 2 times 2 pi, or 4 pi. All right, as we just said, because the initial angle theta was greater than 2 pi, we had to subtract a larger multiple of 2 pi in order to get a negative angle. All right, you could substitute this 2 with a 3 or a 4 or any other integer if you wanted to as well, as long as it's not 1. Okay, so this becomes 7 pi over 3 minus 4 pi. Again, I get a common denominator. 7 pi over 3 minus 12 pi over 3. 7 minus 12, that gives me a negative 5 pi over 3 as my coterminal negative angle. All right, and so that is this angle right here. Again, notice it starts in the same location, right? All these angles in standard position starting on the positive x-axis, negative angles going in the clockwise direction, all right, finishing at this same exact terminal side. There's negative 5 pi over 3. Now, let's talk a little bit more about arc length. We've already learned that the measure of a central angle, so this is an angle measure in radians, one whose vertex is the center of the circle in radians, is given by the ratio of the arc length s to the radius r of the arc. We said theta is equal to s divided by r. So here, for example, I have an angle measure of 2 pi over 3. The measure of this arc length here would be 2 pi, and the radius would be 3. Now, one thing to make note of is that if we were to increase or decrease the radius, the arc length would increase or decrease at the same rate. Okay, we'd have the same ratios. We'd always end up with a ratio of 2 pi over 3 for our angle, for this particular angle. All right, now, we can take this equation and we can rearrange the values and isolate our value s. And we can generate an equation for arc length. So to solve for s in this equation, all we would have to do is multiply r to the other side. All right, that gives us the equation s is equal to r over theta. So we can manipulate our angle measure equation to solve for arc length. One thing to make note of, though, if you're going to use this arc length formula, is that theta must be measured in radians when using this equation. Again, everything in this class should be done in radians unless it's triangles or it specifically says degrees in the problem. So here, let's do a problem. A circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees. Well, when in doubt, draw it out. Here I have a circle. It has a radius of 4 inches, and we want to rotate this through 240 degrees. So that's going to be in between 180 degrees and 270 degrees. So roughly about there. Your pictures don't have to be perfect. All right, there is our angle. Find the length of the arc. That means we need to find this distance right here, this green distance. Well, let's use the arc length formula. S is equal to r times theta. However, theta must be measured in radians. Don't forget that. So right now we have our angle measure measured in degrees. What do we need to do with that? We need to convert it to radians. So how do we convert from degrees to radians? We multiply by pi radians over 180 degrees. Remember, that was our conversion factor. And we can check to see that we're doing it correctly because I have degrees, I divide by degrees, those units cancel out, and we are left with just radians. So this is 240 degrees divided by 180 degrees times pi radians. And again, don't be afraid to plug this into your calculator. 240 divided by 180, hit enter, hit math, frac to get the simplified fraction. And that gives me 4/3 times pi radians, which is 4 pi over 3 radians. There is the measure of our central angle in radians. So that tells us S, the arc length, is going to be equal to r, 4 inches, times theta, 4 pi over 3. And so our arc length is going to be 16 pi over 3 inches. And if you were to plug that into your calculator and multiply out by pi, we would get approximately 16.76 inches. Now again, I always prefer an exact answer. All right, but just to give you some idea of what this quantity is equal to or close to, 16.76 if you're going to plug in 16 pi over 3 into your calculator.